Welcome back, everyone. This is Professor Herring. In this video, we're going to start doing Chapter 16, learning about thermochemistry. We're going to talk about enthalpy changes, how to use and represent enthalpy when it's in a chemical reaction, and energy diagrams as well. So let's begin. So we've already talked about the fact that enthalpy is the amount of heat that's transferred when the reaction is done at constant pressure. We've looked at enthalpy changes for physical changes, such as freezing and melting, vaporization and condensation. And it's also important to know that enthalpies are associated with chemical changes. This can be expressed as a heat of a reaction, and this is the enthalpy associated with any given chemical reaction. Or it can be the heat of formation, and this is a specific type of a chemical reaction, and this is where we form a compound using elements. So this, to summarize, is all chemical reactions, and this is a subset of chemical reactions, a specific kind. When we're quantifying enthalpy for a chemical reaction, we can define the change in enthalpy only. We can never actually measure the exact enthalpy of a given system, but only the enthalpy changes. Therefore, we have to talk about a final minus an initial state. This is the same type of calculation we've done before when determining the change in temperature or change in pressure, etc. And the enthalpy of reaction is defined as the enthalpy of the products minus the enthalpy of the reactants. We know that when the enthalpy of reaction is positive, then that's an endothermic process. And when it's negative, that's an exothermic process. And there's three characteristics of enthalpy that we need to point out. One is that it's an extensive property, or in other words, it depends on the amount of material. So if you're doing a chemical reaction, and let's say that we're blowing up a hydrogen balloon. If you have one balloon, then it's going to give off a certain amount of heat. And if you have two balloons, then it will give off approximately twice as much heat. So it depends on how much of your reactants you have. The enthalpy for a reaction also will change sign if you reverse the reaction. So if we were to somehow be able to unblow up the balloon, then that would, instead of giving off energy, it would absorb energy. One way of writing this is the enthalpy forward is the negative of the enthalpy reverse. And then finally, enthalpy depends on what state our reactants and products are in. So we might have the enthalpy of reaction where we have a solid going to a liquid is going to be different for the enthalpy of reaction of a solid going to a gas of that same substance. Nope, that should be gas. Okay, so let's take a look at an example of each of these characteristics. So let's say that we've got this as our chemical reaction. This is the combustion of methane into carbon dioxide and water. And as written, that reaction will give off 802.3 kilojoules if we have a mole of methane, 2 moles of oxygen, 1 mole of carbon dioxide produced, and 2 moles of water produced. So because enthalpy is an extensive property, if we double the reaction, we're going to double the energy that's given off. If we reverse the reaction, instead convert carbon dioxide and water to methane and oxygen, that's going to reverse the initial enthalpy. And then finally, the states of matter matter. So in the initial reaction, we're forming water as a gas. Here we're forming water as a liquid. And notice that there's a difference in enthalpy. In other words, we know that because gas is higher than liquid in terms of its energy, that by going from a gas to a liquid, we released energy. And therefore, more energy is released for this last reaction compared to the first reaction. Thermochemistry is the study of energy changes in chemical processes. And what we mean by, so chemical energy is the energy, potential energy associated with bonds. We've talked about chemical bonds and intermolecular forces. And so when you have an attractive interaction between the nuclei to form a bond or between two different molecules to form an intermolecular force, then that releases chemical energy. So in this case, where we have hydrogen and oxygen reacting to form water, that's a very exothermic reaction. What we see is happening is that the bonds between the hydrogen atoms are breaking, and the bonds between the oxygen atoms are breaking. And instead, we're forming bonds between oxygens and hydrogens. If we were to look at this in terms of an energy diagram, one way to depict that is showing our reactants and our products. And in this case, because it's an exothermic reaction and the heat's lost to the surroundings, we would indicate off to the side of that reaction what that enthalpy is. And we call this a thermochemical equation. And that's where we have a balanced chemical equation that includes the enthalpy change. Another way of writing this would be hydrogen plus oxygen yields water plus heat. Or if it were endothermic, if we do the reverse, that would be water plus heat yields hydrogen plus oxygen. All right, why don't you now think through this on your own and try and answer it. So pause the video and come back. Welcome back. So in this reaction, we're looking at hydrogen peroxide. And it says that the temperature of the hydrogen peroxide solution increases as it decomposes into water and oxygen. Based on this information, which energy level best describes the enthalpy level of the products? Well, we know that exothermic processes, they give off heat. And so if we're observing the temperature with a thermometer, it will observe an increase in temperature. That means then that we have to have a negative enthalpy of reaction. And so our enthalpy of our products must be lower than the enthalpy of our reactants, which means that it has to be answer choice C. Okay, let's try one more problem. So how much heat would be released by the reaction of 12 grams of methane reacting with 22 grams of oxygen to form liquid water and carbon dioxide? This is applying what we've learned already about reaction chemistry and now adding in this element of thermochemistry. So you should be able to do this one on your own. Pause the video and try it first, and then come back and I'll walk you through a solution. Welcome back. So, as we've done before, what we want to do for these types of reactions is indicate our initial conditions, what we're given. We've got 12 grams of methane, 22 grams of oxygen. And since we're given masses of each, we have to evaluate which one's going to be the limiting reactant. So we need to know the number of moles, and so the connection is going to be the molar mass. Methane's molar mass is 16 grams per mole. Oxygen's molar mass is 32 grams per mole. So we want to know in the end how much heat's released. So what we can do is we can see that there's a relationship here. That for this reaction, we have 890.3 kilojoules, and this is per reaction. So this is going to be per mole of methane, or per 2 moles of oxygen. And so we can use that in the sense to essentially evaluate how much product is being formed. So for methane, we have 12 grams using the molar mass of 16 grams per mole. Oops. And the fact that it gives off 890.3 kilojoules per 1 mole. That's going to release 667.73 kilojoules. For oxygen, we have 22 grams of oxygen. It's at 32 grams per 1 mole of oxygen. And it releases 890 kilojoules as well, but that's per 2 moles of oxygen. And again, that's coming from these coefficients in the balanced chemical equation. And this is the same thing that we would do if we wanted to find out how much carbon dioxide or water were produced. The only difference is that we're using the enthalpy of the reaction. So in this case, this produces 306 kilojoules. Okay, so it's clear that our oxygen is our limiting reactant because it produces the least. And then, does this answer the question? Well, we want to know how much heat will be released in this reaction. So yes, we've answered the question. Now, why, in this case, do we have positive versus negative? Well, this is another way of saying this is that there's 306 kilojoules released. And if you look at the wording, it's asking how much will be released, and therefore it's implying that all of these are negative values. So you just want to pay attention for that type of wording. Okay, that's it for this video. Thanks for watching. If you have questions, you can ask on Piazza and office hours or recitation.